Good afternoon everyone. So we'll discuss structure of atom. So in the last session we have discussed periodic properties, periodic classification and properties, and we have also seen previous year questions of biotechnology, chemistry questions in IIT JAM biotechnology exam right now. So now before starting this chapter, I just wanted to show you what kind of questions and how the questions are asking in the exam first. Let's have some clarity over the questions first. Okay, so now see here they are asking about ground state energy of hydrogen atom is this much. It means something related to, see Balmer's, it is something, it is related to Bohr's atomic model. Okay, so I will explain you Bohr's atomic model. If you look into the syllabus of this IIT JAM chemistry, so they have mentioned just Bohr model. Okay, so that important topic is Bohr model from structure of atom. Okay, along with that just look at the other questions also. So look here also hydrogen spectrum, yeah, this is also will study in Bohr's atomic model. Okay, and the next thing is, see here distance, something related to, see again Bohr's radius. Okay, so it means Bohr's model is one of the very important topic we should consider from these questions. Okay, and the next, see they are asking about calculate the wavelength of alpha particle. Okay, so along with the Bohr's model, even though they have mentioned only Bohr's model in the syllabus, so they are asking questions from this Planck's quantum theory and de Broglie wave equations. Okay, I will explain you that also. Okay, and the next thing, see again Bohr's atomic radius, de Broglie wavelength. Okay, it means we need to have some idea over other topics also. Again something related to quantum numbers and subshells like P shell, SPDF subshells are there now. So regarding that also they are asking. So it means we need to study quantum numbers also. Okay. Again nodes, again related to quantum numbers. Okay, so from by looking all these things, what we got to know, what are the things that should be discussed, that should be focused in this structure of atom. First one is Bohr's atomic model. This is a very Bohr's atomic model. Okay, this is very important one, and along with that de Broglie wave equation. Okay, and the next along with this Planck's quantum theory, okay, and also quantum numbers. Okay, so if you have already came from a chemistry background of 11th 12th class, you have seen these things during that time. Okay, so now I will be starting this chapter with a very basic one. Okay, so first of all what are the basic terminology we will be using in this chapter, we should know that, then we will go to this. Okay, so that my intention is to understand by every student, those who are from non-chemistry background also. It means they might be left their chemistry around some 3-4 years back. Okay, so I am focusing on them also. So that's why I am coming with very basic things first. Okay, so now what we know, atom. Okay, atom considered like a spherical shape. Again we know that at the center of the atom we have something called nucleus, around which electrons will revolve. Okay, so what are the constituents in this nucleus? Protons and neutrons. Okay, and what about the charge of proton? Positive, and neutron is 0, no charge, neutral. And here these spherical shapes, I have circular paths I have mentioned. So what is this? Electrons will revolve in this, around this nucleus where it has negative charge on it. Okay, so something like this I have mentioned. Discovery of subatomic particles. What are the subatomic particles in the atom? Electrons, protons and neutrons. Okay, so those are having no charge for neutron, proton having positively charged, electron negative charge. Okay, now tell me who discovered this electron, proton and neutron, because we don't know from where he can ask the question. Okay, let us have some look over that. See, we are studying that atomic models now, like Bohr's atomic model I am saying. Okay, Rutherford's atomic model I am saying. Like this, there are some scientists like Thomson. So what he did, he discovered the electron. What he did, he discovered the electron by cathode ray tube experiment. Okay, we'll see that, have some small glimpse on it. And the next, Rutherford's atomic model we have. Thomson, what he did, he discovered the electron. After him we have Goldstein. What his name? Goldstein discovered proton. Okay, and next James Chadwick, what he discovered? Neutron. Okay, these names you have to remember. Okay, I will show you regarding the information about electron, proton, neutron. Next we have Rutherford's atomic model. Now these guys, Thomson, James Chadwick, Rutherford, Goldstein, they discovered subatomic particles. Now how these subatomic particles are arranged in the atom, that we should be clear now. So the person who proposed that is, first one is, here we have like Rutherford we have. Before this we have what? Plum pudding model. So what we have studied that atom is considered as something like this, in a like considered as a watermelon. So where the positive charge is uniformly spread all over the atom. That watermelon, if we see, if we cut the watermelon, the red color part, plum is there now, that is what? Neutrons, I mean protons, like positive charge spread uniformly throughout the atom, in which electrons are embedded. It means the seeds of the watermelon are there now, so those are considered as electrons now. So in the region of this positively charged spread over positively charged protons are spread now. So in that we have what? Electrons like seeds in the watermelon. So overall atom is neutral. So electrical neutrality is maintained. So this is what we have studied in watermelon model. But later when he did, this Rutherford did his experiment, okay, gold foil experiment, I will show you, okay. So that law got failed because his practical experiment is giving some completely different from that scenario, okay. After that we have a legend, Bohr's atomic model we have. We need to study this more clearly, and then later we have Planck quantum theory for explaining particle nature, wave nature, all these things, because of light has dual nature right now, wave and particle. So we have to study Planck's quantum theory as well as photoelectric effect. Let's have some small glimpse over it. Next, de Broglie wave equation, and this Heisenberg is not that much important as of the questions if we see, okay. Schrodinger wave equation also not much needed here, okay. So now tell me, what are the fundamental particles we have? Electron, proton, neutron. Who are the discoverers? J.J. Thomson, Goldstein and Chadwick. Okay, symbol we are using EPN, electron, proton, neutron. Okay, so what is the charge of electron? 1.602 into 10 power minus 19 coulomb. So how do we got this charge? By doing Millikan oil drop experiment. What is that? Millikan's oil drop experiment. Okay, from this J.J. Thomson, he given charge to mass ratio of electron, okay. Millikan given what is the charge of electron. So by together we can find mass of electron. Is that clear? Now what is the charge of electron we have? Minus 1.602 into 10 power minus 19 coulomb, you can remember. Next, what is the mass of electron? 9.11 into 10 power minus 31 kg. Now I am also asking you, what is a charge to mass ratio? Okay, just find from this. Okay, now see, if I consider this is the charge of absolute charge, if they ask, you should take like this. If they ask relative charges, relative charge means this complete value considered as 1. Since charge negative sign is there, so put it in negative. So I can say relative charge. So now relating to this, what about proton? So proton has same charge but with a positive sign, same magnitude but positive sign, okay. So now I can consider relative charge as +1. And what about the mass? 1.67 into 10 power minus 27 kg. Similar to that, then we have neutron given by Chadwick, okay. So symbol and charge is 0, relative charge also becomes 0. And what about mass? 1.67 into 10 power minus 27 kg. So now what is the question we can expect from here? There is a small question I can create from this data. See, arrange them based on charge to mass ratio. Arrange in increasing order of charge to mass ratio of electron, proton, neutron. It's a very basic question I can create from this. So tell me. See, I have applied mod just to avoid that confusions of negative positive symbols. Okay, tell me. First of all, let us do for electron. So tell me, for electron how much we can see? See, I am saying charge to mass ratio, no? Let us take this relative charges in order to avoid all these big numbers. Okay, so so here charge to mass ratio of electron I am asking. So how do you do? So charge is -1 means mod is there now, so you can write just 1 by what about its mass? So 9 point this much is there now. So 9.1 into 10 power minus 31 kg. Okay, you just write it for some time like this. Okay, now I am saying charge to mass ratio of proton if I ask, that will be 1 by 1.67 into 10 power minus 27 kg. Okay, now what about charge to mass ratio of neutron? 0 by something, 0 by something becomes 0 only. So now see here, we know for neutron it is 0, charge to mass ratio of neutron is 0. What about these two things? Compare which is bigger value, which is smaller value. See, this denominator is smaller value, therefore I can say charge to mass ratio of electron will be big. Denominator this is small now, yes or no? So what is the order from this information? We got charge to mass ratio of electron greater, then here you can observe, so proton and least is neutron. Clear? This is the thing you can note out of this. Clear? Now who discovered neutron? I told you Chadwick, right now. So now just look at this. So what is the reaction, they may ask you, what is the reaction involved in the discovery of neutron? So it is a radioactive reaction. So when beryllium atom is bombarded with helium nuclei, so what is this helium nuclei? I can say this is an alpha particle. Okay, so alpha particle has 2 protons and it has a mass of 4, mass number as 4. So they may indicate like He plus 2 or alpha like this, both are alpha particles only. Okay, so when this alpha particle bombarded this beryllium, so what we will be getting? We will be getting a extra particle along with the carbon, which we can say it as neutron. Okay, this reaction is also important. Okay, now clear with this, just write this reaction also. Next, see, done with this? So now just tell me what is the orders of mass of electron, proton, neutron? Mass of electron, mass of proton I am asking, mass of neutron I am asking. So which is greater here if you look at the values? Relatively, with a small amount, mass of neutron is bigger, just check. Okay, so I can write like this, almost like this, either bigger or almost equal or bigger, little bigger, no? So I am using that symbol. And here like this, it is not just one, it is having a large gap between mass of electron and proton. That's why while calculating atomic weight, what we will take? We will take sum of weights of number of protons plus number of protons and neutrons, but not electrons. For example, carbon atomic number 6 you are saying, mass number is 12. Why this 12? So it has 6 protons plus 6 neutrons. Like this only you are taking, you are not considering electrons here right now, because relatively it is negligible value like that. Okay, and one more thing if I want to express here, so how many times mass of proton is bigger than mass of electrons? So mass of proton will be almost approximately 1837 times bigger than the mass of electrons. Mass of electron, is that clear? Similarly, mass of neutron if I ask, this is almost approximate value 1840 times mass of electron. These are all the information that are required for you as a basic thing. Okay, Hope up to here it is clear. Move forward. So here we have seen already this Thomson's model. Next, Rutherford's atomic model, what it is? He has taken a gold foil and he used some alpha radioactive source which gives alpha particles from this. So alpha particle means what is the charge we have seen? It has helium nucleus, means it is having positive charge like 2 4. Okay, it has 2 protons in it, so positive plus 2 charge right now. So when these positively charged species are coming from the source, when they are bombarded, like when they are passing through this gold foil, what he observed, see, most of the alpha particle rays are going without any deflection, they are entering from it very easily. But there are few alpha particles having some deflection with either small angle or with large angles, and few alpha particles are exactly going back by retracing its original path. It means they are exactly going 180 degrees back. So what this experiment shown him, what is the observation he's got from this? So he considered that there is a small region or small space in an atom where the positive charge is concentrated. He called it as nucleus where protons are concentrated. So why he is saying protons are concentrated? Because alpha particles are also positive, that protons are also positive. So when they are going in the same direction or same path of that nucleus, what happens? That protons, so repulsions are taking place, that's why it is retracing its original path. Okay, if it is going beside that, there is some small deviation, that's why they are having some angle of deflection like that. Okay, yeah. So now how he observed this? What is this extra boundary here? That is a photographic plate or fluorescent material. Generally it is zinc sulfide kind of material. So what happens, this alpha particle when hits the surface, there will be some fluorescence observed. Okay, so these are the observations we have did in that. Okay, see, most 99% of the alpha particle passes through it without any deviation, but few were deflected with some angle and very few were deflected with 180 degrees. It says that positive charge is concentrated at a very small portion of that particular atom. Okay, and remaining portion is hollow space, he considered like that. Okay, it is found that the size of, if the size of atom is in the orders of 10 power minus 15 meters, orders means maybe in this range, something like 2 into 10 power minus 15 or 3 into some kind of multiplication is there. So it is in the orders of 10 power minus 15 meters. If this is the size of atom, then next nucleus size will be, see, I am saying this is 10, atom size is 10 power minus 10, then the nucleus size will be 10 power minus 15 meters. Okay, so you can remember these two values. Okay, so if this is the size 10 power minus 15, this will be in the orders of 10 power 10 for the size of atom. Okay, next. Yeah. So what are the drawbacks here from the Rutherford atomic model? See, from classical mechanics what we know, if any charged body is under motion in the influence of attractive forces continuously, what happens? It loses its energy. See, proton, electron, if it is revolving like this around the nucleus, both are oppositely charged, no? So now what happens? So after some time, that moving particle should lose its energy and follow its spiral path and should fall into the nucleus. But is it happening? If that happens, atoms should get destroyed, but atoms are being stable. It means there is some misconception or some no proper explanation in this theory, right now. So see, so the electron follows spiral path and finally falls into the nucleus. That atom should get collapsed, but it is not happening. Okay, now it says nothing about, this is a one drawback. Second drawback, it says nothing about structure of atoms, how electrons are distributed around the nucleus. It means we are studying now like s orbital this many electrons, p orbital that many electrons, that distribution is not given here. So to explain these things, next the legend Bohr came with his explanation, Bohr's atomic model. We will study about that. Okay. So he considered this point as a main drawback. He explained it in his theory, atomic model. Okay. Next, there are some other small terms also, special terms we use in this chemistry in atomic structure. We need to know. So what is atomic number? It is given by number of protons in an atom. Okay. So for an atom, if I say, see, atomic number is equals to number of protons, or you can also number of electrons also. Okay. But in case of ions, if I say Na plus ion is there, so in this case you should not say it is equals to number of electrons, because here electron is removed. So in this case you should say only for protons, number of protons only. Okay. So that is the standard way. For sodium 11 we are saying, it means it has 11 protons and 11 electrons. So for Na plus, atomic number remains same. It means what? Number of protons will remains same, but electrons only take part in the chemical reaction. Okay. Next, what about mass number? See, the elementary particles, electron, proton, neutron present in the nucleus of an atom are collectively known as so neutrons and protons are collectively known as neutrons. So mass neutrons and protons collectively known as nucleons. Okay. So mass number symbol is A, is sum of protons plus neutrons plus protons. Okay. Next, okay. See, how do we represent an atom? For example, this is a symbol of an element, let us say. Okay. So here I will be indicating, see, atomic number with the symbol Z. Here I am indicating mass number A. Okay. And you know, if there is any charge, we should indicate here, like plus, minus numbers if anything is there, like zinc is there. So plus 2 you are writing, something like that. Okay. Now atomicity, here this space indicates what? Atomicity. For example, O2 you are writing. So number of oxygen atoms 2 now. So here it represents what? City. Okay. Let us indicate this symbol with some P. Okay. So this is what? Charge. This is mass number and this is atomic number. Okay. And this is symbol of element. This is a standard representation. Okay. Next. There are other terms also, basic terms. What are isotopes, isobars, isotones, isoelectronic species? Okay. So they may ask in the question in the exam, like what are the isotopes, by giving 4 options. They may mention some statement based questions. Isotopes are the species which have same different mass number. Like that they will alter the options and they will give us. Okay. So now see here, first isotopes are what? Isotopes are the atoms of same element having identical atomic number but different mass number. For example, carbon has isotopes like we are saying C12, C13 and C14, right now. So these are the 3 isotopes for carbon. See, for them number of protons same but neutrons are different. So isotopes are differ in their number of neutrons, you can say. Therefore their mass number becomes differ. Okay. Yeah, hope it is clear up to here. Next. Next, what about isobars? See, atoms of different elements having different atomic numbers. Okay. But same mass number. So we know different elements means different atomic numbers, but they have same see here mass number, see here for potassium and argon. So here atomic number 18 and 19. Okay, it means number of neutrons here, how many are there? So 40 minus 18 you can do. So neutrons are 22 and here 40 minus 19, 21. Okay, like they will ask number of neutrons present in this and but if you look at their mass numbers, everyone is having same mass number. Now what is balancing them? Number of neutrons is balancing that mass number. Yeah. Next, isotones, the name itself saying tones, neutrons, okay, same number of neutrons. See, atoms of different elements which contain same number of neutrons are called isotones. Okay, so now see, for these elements 16 for chlorine and sulfur, if we say atomic numbers, see mass numbers we are taking, just remove here, you will 37 minus 20, 17 you will get 20, and here also 36 minus 16 gives 20, so same number of neutrons. So isotones, isobars, isotopes is over. Next one is, I am saying isodiaphers. These species have same n minus p value. What they have? Neutron minus proton difference, if you take, they will be having same values. Okay, just write it as a definition. Okay, then next. Next, what about isoelectronic species? The species containing same number of electrons. For example, here. Okay, now isoelectronic species is covered. In the last class I have explained radius properties, periodic properties, radius, atomic radius, ionic radius. Now arrange these species based on their size. Based on their size. What is the size order for these ions? Size. See, so that's why I told you to revise the topic. See, how many electrons are there here? 10, here also 10, here also 10, all of them are 10. That's why we are calling them as isoelectronic species. See, negative charge means add that many electrons to its atomic number, like atomic number of oxygen is 8, minus 2 charge, so add 2 electrons becomes 10. Here positive charge means remove that many number of electrons. Aluminium 13 plus 3 is there, remove 3 electrons becomes 10. Total 10 electrons. Clear na? Now what I told you, see what I told you, size is inversely proportional to nuclear charge. Did we discuss that or not? Where do we have more nuclear charge? More positive charge is here. It means its atomic number is 13, having only 10 electrons. Its atomic number is 8, but having 10. So where do we have more positive charge? Aluminium, na? So smaller size will be for aluminium. So I can write aluminium is smaller, then magnesium, then sodium, F minus, O2 minus. Did we discuss this or not? I have repeatedly discussed these things, like A plus, because like these questions we have seen in the previous paper. So tell me, what is the size order? I have asked like this also. What is the order? Like this, no? Very basic questions these are. So like you do not want to use any your energies or anything, just choosing the option is the only thing you need to do here. Okay. Next, now let's have some idea over these electromagnetic waves and all. Okay. So this radiation, electromagnetic radiation we are saying now, it contains two components. One is electrical component and magnetic component. See, we have electric field component like this, okay, and here perpendicular to that we have magnetic field component like this, Okay, so they are perpendicular to each other, electric field, so magnetic field component perpendicular to each other, and they are perpendicular to direction of their propagation. If they are going like this, so here we have one electric field and here we have magnetic field like that. Okay, so they do not require any medium to propagate or travel. Okay, so what are the characters of these waves? So I hope you know that wave contains one crust and one trough like this, right now. So you can indicate positive and negative symbol also. Okay, this height is there now. What we call this height? Amplitude. Okay, or this depth is there now. This is also amplitude. The height of a crust or depth of a trough is its amplitude. Okay, this complete cycle is considered as one wave. Okay, so here if I ask half wave, yes or no? So if this is a full wavelength lambda, so here you should say lambda by 2. Okay, so this and this. So how many waves are there in this? 1, 2, 3. Okay, like that. Okay, so now amplitude is done. What about frequency? So number of waves passing through a point in 1 second. See, if wavelength is smaller, see, I am drawing two types of waves here on the same line. One is with bigger length and one is with smaller length. See, this is also a wave and this is also a wave. So now tell me, what is the frequency definition? The number of waves passing through a point in 1 second. Now tell me, this wave will travel more or this waves will travel more from a point in 1 second? Smaller wave. So what I can say, wavelength or frequency is inversely proportional to wavelength. Smaller the length of a wave, greater is its frequency. From this basic understanding, can I write a relation like this? Small wavelength, bigger is its frequency. So we have a relation like this. So now I am removing this proportionality, I am writing C by lambda. Basic understanding it is. Okay, so remember that frequency equals to C by lambda. This is also one important relation. You can expect a question in physics or chemistry or somewhere else. Okay. So now C we have written now, that is nothing but velocity or speed of light we are saying. What is the speed of light? 8 meter per second. Okay, so here I have, that is speed of light. Okay, and like this basic relation, what is the relation between angstrom and meters, angstrom and nanometer, nanometer to centimeter, these are also important things you should focus. Okay, now where electromagnetic spectrum. So here we have range of areas. So what are the things we have? Like gamma rays, X-rays, UV, visible, IR, micro, radio waves. So what are those? Gamma rays, X-rays, UV, visible, IR, micro, radio waves. Okay, so now these are highest energy rays. So what I am saying, if we go like this, energy decreases. Okay, and you know this is high frequency. So I can say frequency decreases as we move this side. Okay, so what we got the relation between frequency and wavelength? Frequency C by lambda na inversely proportional. Okay, so this is low wavelength. Can I say low wavelength? And here lambda increases as we move this side. So this is high wavelength. Okay, clear na this basic understanding? I hope you know. And what is the range of visible region they will ask? So here you can see 380 to 760 nanometers, you can remember. What is the range of visible spectrum? 380 to 760 nanometers. Okay, now once again, what is the frequency order? Highest to lowest.
Yes,
tell me. Gamma, X-rays, UV, visible, IR, micro, radio waves. That's it. Okay, remember this. If they ask in wavelength order, give it in opposite order. Radio waves will be highest one. Okay, now give answer for these questions. The radiation with maximum frequency is? Huh? Maximum frequency is for X-rays. Gamma is not there, so X-rays. Okay, now arrange them in the order if I ask. High, first high to low. A, U, B, C, A, C, D, B. Okay, basic. Okay, next. This is also one basic question we have. Tell me. So an element in +2 oxidation state has 24 electrons. The atomic number of element and the number of unpaired electrons in it. +2 means 24. So I have an element, let us say M is an element having +2 charge. Okay, so it means if I go to its respect to M, this is the ion, this is atom. So here it has 24 electrons. Now I adding these 2 electrons back to it becomes 26 electrons. So in atomic state we know its atomic number is equals to number of protons, or I can also say number of electrons also. So its atomic number is how much now? 26. So 26 is there here, 2 options. So for 26, so tell me, I just wanted to ask you, what is atomic element with 26 atomic number? Iron. So I told you in the first class itself, try to learn first 30 elements. If you know, just revise them, then you can get more confident over questions and all. Okay, so now what is the electronic configuration? So no need of writing all these things. Now you just write argon 18, next 4s2 20 over, next d orbital electron, na, this d shell like d block element now, so d 3d 6. See, I will tell you, follow one blind trick. Okay, so 26 now we have one 4s and 3d, so write this 2 here and 6 here. Okay, now tell me for manganese, what is the atomic number? 25. Just tell me 4s 3d. Tell me 4s 2 3d 5. It's working. Okay, now tell me for chromium. Chromium 24. Tell me 4s2 3d. If you write like this, this will be wrong. Okay, because we know how many d orbitals are there. D orbitals like this. 5 d orbitals are there now. So whenever there is possibility for half filled and full filled configuration, those are stable. So that's why gain stability. One electron from here jumps to here. It becomes 4s1 3d5. Just remember here. This is okay. Now along with this, you can also have one more thing. Now tell me for nickel, atomic number is 28. So just tell me 4s 2, whatever the number there, you just write it. Okay, so now I think half filled possible d5, full filled possible d10. So d10 means if I say copper 29 now in this case you should think again you have to think about configuration. Write it 9, you write as it is. Now if I give one electron, it becomes fulfilled na. So again that's why a variation in electronic configuration. These 2 things you should remember, chromium and copper. Remaining everything you just use its atomic number, write that many electrons, this first number in s orbital, second number in d orbital. That will be your answer for 3D series elements. Hope this is also clear. Yes, and anyone in the live, if you are really following the class and everything is going well, please click on the like button. If not, feel free to express in the chat box. Yes. Okay. Now tell me for iron. So this is the electronic configuration we got. So what I can write? Like this. Okay. 2 here, 1 2 3 4 5 6. Okay, how many unpaired electron? 4. So here we have, so go with option B. Clear na? Huh. I hope you know that Hund's rule or Hund's rule.
Maximum multiplicity.
It means we should give 1 electron here as we given first. Later you pair up if any extra electron. See, if I have only 5 electrons, first give 1 electron. That 6th electron should come for the first again for pairing, like that. Clear now? Yes. Next, particle nature of this electromagnetic radiation. See, we know light has dual nature now. So how this wave nature is explained? How the wave nature is explained? By its terms called diffraction. You know what is diffraction? If you torch a light, what happens? If there is any obstacle, so light will bend around that obstacle now. So I can say the bending of light around an obstacle is called diffraction. Okay. Next, interference. What do we mean by interference? See, for example, I have two waves. Let us say this is wave number 1 and I have wave number 2, like this. Okay. So now when these two waves are merged, what happens to the resultant wave? We will get a resultant wave with additive of these two amplitudes, like a bigger one. So this is called what? Interference, like constructive interference, destructive interference. We will be studying in somewhere in physics. Okay. These are the two properties that explains wave nature of light. Okay. Along with this, we have other properties like reflection, dispersion. Light will disperse now if we torch it. Now see, Planck's quantum theory. Here we need to study about particle nature. First one is Planck's quantum theory. So according to this theory, energy can not be observed or emitted continuously, but it is emitted in the form of small pockets called quanta. For example, I have a source which is emitting energy. You know, black body, something like this. Anytime hear that? What is it? It is an ideal body. Okay, assume it is an which can able to absorb or emit all the types of radiation at all frequencies and temperature. Okay, so this is a source which is emitting radiation. Okay, so now these emissions will be observed in the manner of some discontinuous manner like this, in the form of small packets like this. Consider this is as a one packet, another packet, like that. Okay, so this small packet of energies are called photons, and here see quanta in case of light. See, form of small packets called quanta. Quanta in case of light is called photons. So I can say this as photons. Okay, the energy of each photon, the small packet is there now. The energy of this small packet, the energy of each photon directly proportional to. So I can write E is proportional to frequency nu. Okay, from this E equals to h in nu I can write. So this nu h is what? Planck's now, Planck's constant. What is that? 6.626 into minus 34 joule second. You can take this. Okay. So now from here again I can write h as it is. I want to write in terms of wavelength, means c by lambda. We already discussed now, nu equals to c by lambda. If I want this speed, I can say nu into lambda. Okay, when you multiply frequency with wavelength, you will get speed. Okay, c in the case of light. So other speeds also you can calculate if they give frequency of that particle and wavelength of that particle. You can find the speed of that particle. Okay, hope clear, everything is clear up to here. Yeah. So what is the value of c here? 8 meter per second. Okay, you have these two things, this value they will mention. Okay, let us do one or two questions. Yes, here I have a question. So calculate the energy of photon emitting or having wavelength this much. See, here you have seen these formulas now. This is for 1 photons. If there is n photons, I should take it as n h nu. This is for 1 photon. If there are n photons, energy means n into h nu. Now do it, calculate the energy of a given photon of wavelength, these two things. Okay, I will do for 6000, you can do for this first one. So E equals to h c by lambda I can use. So 6.6 into 10 power minus 34 joule second into c value meter per second by lambda how much I am doing for second one, you can do for first one. Okay. So how much you will get? See, this will be how many times? 10 power minus 24. Okay. So now I can remove these 3 zeros by writing like this, it becomes 10 power minus 24 plus 3, 27 I can write. Okay. And this is 2 times and this is 1.1 time. Okay. So how much we got? 1.1 into, see, they have given in terms of angstroms now. So I can write this in terms of angstroms is there now. So 1 angstrom how many meters? Minus 10 meters. Right now, so this meter cancelled. Okay. So this becomes 10 power minus 17. Okay. So 1.1 into 10 power minus 17 joules. See, second also cancel joules. So your unit should not be remained, any excess unit should not be remained. If it is there means you are doing something wrong here. See, second per second cancelled out, a joule is as it is, meter cancelled out, we are remaining only with 1 unit, joules is a unit of energy. Clear now? So this is 2 times, this is 3.3 more, this is 3.3 times. Okay. Now tell me for the other one, you can easily do that. .6 into 10 power minus 90, no? Okay, you can just do, you will get the problem. So, next, what about photoelectric effect? See, this is a metal surface. So metal surface is nothing but it contains metal atoms, no? In metal atoms we know metal atom contains electrons, no? So metal like atom contains these electrons. Now I am using some light source, I am incidenting that light source on this metal surface. Now what happens if we supply sufficient amount of energy to this metal surface, the ejection of electrons takes place. The ejected electrons can be considered as photoelectrons and this complete process is electric effect. Just read this. See, when a radiation with certain minimum frequency or sufficient energy, I can say, strike the metal surface, the electrons ejected from the surface are photoelectrons and phenomena photoelectric effect. Is that clear up to here? See, for example, see if this is a metal surface containing this electron. So for ejection of this electron, it requires some energy, yes or no? So let us say this electron requires some 10 joules of 10 electron volts of energy, let us say. Now I am supplying only 9 electron volt. Will this ejection of electron takes place? No. I can say no photoelectric effect in this case. Okay. Now I am supplying 10 electron volts of energy. In this case, takes place. Okay, takes place. Now I am supplying 12 electron volts of energy. Photoelectric effect takes place, ejection of electron takes place because it requires only 10 joules. So out of this 12 joules, 12 electron volts, 10 electron volts is used for ejection of electrons right now from this metal surface, and extra how much we have now? 2 electron volt of energy is extra. So now this extra 2 electron volt is taken by that ejected electrons. See, from metal surface by supplying 10 electron volt, 2 electron will get out now. So this will take if any extra energy is supplied. Okay. Now it means what you understood from here. So supplied energy is utilized for 2 processes. One is for ejection and the second one is taken by the electron. This electron will take this extra energy and convert it into its kinetic energy. So the extra energy will be converted into kinetic energy of that photoelectron. So what I can say, E supplied will be equals to, I can say for ejection we require some energy, that is called work function, or simply threshold energy also I can say. Work function I can represent with phi. Some books also gives with this omega symbol. Do not get confused. Okay? Plus what I told you, one is for work function, another one is for kinetic energy of these photoelectrons. Is that clear? So now work function is nothing but that is also energy only, na? See, out of 12, 10 is utilized. It means 10 electron volt, that is also energy only. So I am writing this E supplied as h nu. E is equals to h nu, just now we written now. So here also I can write nu only, but to differentiate I am writing h nu. Okay, plus Ke I am writing. Okay, so nu naught here it is what? Frequency of applied light. Okay, this is called threshold frequency. It means we should send, if applied frequency, nu is what? Applied frequency I am saying. If applied frequency is less than threshold frequency, so is there any photoelectric effect or not? No PE. If applied frequency equals to PE takes place, but kinetic energy of photoelectron will be 0. If applied frequency is greater than threshold frequency, PE takes place, photoelectric effect takes place, and kinetic energy of photoelectrons will be greater than 0. Clear now these three things? Next. This is the instrumentation we can set up, I can say. Now we have studied ionization energies in classification of elements. Do you remember that? Periodic properties. So now tell me, we know alkali metals have lower ionization energies in the periodic table, right now? So now tell me what are the elements? Sodium, potassium, rubidium, cesium. I am taking these elements. So tell me which element having lower ionization energy? Down the group size increases now. So we can easily pick out the electron from the larger element. So from cesium we can easily remove the electron. So ionization energy is lower for cesium. Why I am discussing here? Because we are studying about photoelectric effect now. So here we will be using metal surface, right? So which metal is very suitable out of these four? Last one. Why? Because in order to happen this photoelectric effect, that should release the electron easily without any much energy, right now? So that will be possible with cesium. So now I will be giving you one graph. You need to identify. See, what is the final equation we got? H nu equals to H nu naught plus K. Okay. So now I am applying this nu equals to nu naught plus Ke by H. Can I write like this? Just divide complete equation with H. Got it up to here? Now next, nu equals to nu naught I have now. So I am writing this 1 by H into kinetic energy plus nu naught. Can I write like this? Yes. After this, look at this. Do you know graphs? Drawing the graphs. See, y equals to mx plus c type graph we have, right now? So what is our y? Frequency, okay, and our x is kinetic energy. Clear up to here? Now we have an intercept here with a positive symbol. Right now it means this should be here somewhere, intercept, and slope is also positive. So we should get a graph something like this. Okay. So now tell me, is this graph is clear or not? What is the slope? 1 by h. What is the intercept? Nu naught. Up to here, is this clear? So nu naught means threshold frequency we discussed. Now from this threshold frequency, I just wanted to ask you one question based on this. I am drawing a graph something like this. 3 lines I am drawing. So line 1, 2, 3. Okay, this graph is nothing but nu versus K. I am giving you 3 elements, potassium, rubidium, cesium. Now arrange these 3 elements over here. Third line is for cesium. Why it is for cesium? We discussed minimum frequency. Minimum frequency means minimum energy. So minimum energy required for which element? Cesium. That is easily giving na lower ionization energy right now. So this is lower gap, lower threshold frequency. So that's why it is for cesium. Then this is for potassium. Clear? Yeah. Okay. So there are 2 statements you should remember in this photoelectric effect again. What are the 2 statements? One is threshold frequency for a particular metal will remains same. What I am saying, threshold frequency of a particular metal remains same, because if I talk sodium metal I have, or some potassium metal I have, or some rubidium metal I have, its frequency threshold, the minimum amount of energy required to eject electron from this metal surface will remains same right now. So now if I increase the applied frequency, we know nu naught will remains constant for a particular metal. So if I increase this applied frequency, what happens in this case? This remains same, but kinetic energy of photoelectron increases. So you can write, if applied frequency increases, kinetic energy of photoelectrons increases. Can I write this statement? Yes. Now one more statement you need to remember here is, you know, brightness or intensity, both are same only here, by brightness, intensity. For example, this is a metal surface. This is a metal surface. Metal surface I am saying. See, I am using a light of lower brightness and I am using a light of higher brightness. Let us use like this. So brightness or intensity is nothing but the number of photons present in that. Okay. So here if I say lower brightness, it means it contains low number of photons. So remember here, each photon eject 1 electron each time. Only for ejection of 1 electron, how many photons it can take? 1 photon ejects 1 electron. Okay. So if I am saying that I am increasing the intensity of light, so what does it mean? We have more number of photons in that light. Yes or no?